Welcome to Maths Weekly. Today I will be introducing hyperbolic functions. So let's start off by looking at a small bit of trigonometric functions. We know that it's based on the unit circle meaning a circle with a radius of 1 and centered at the origin in the Cartesian coordinate system. We also already know that the x-coordinate is cos t and the y-coordinate is sin t when the angle is t. The interesting bit is that when you sub in cos t for x and sin t for y in this formula for a unit circle, you end up with a familiar identity. Cos squared t plus sin squared t equals 1. Let's start to take a look at hyperbolic functions by thinking of a hyperbola. What I have here is only part of a hyperbola where x is greater than 1. So you already have a rough idea of what a hyperbola should look like. A standard hyperbola has Cartesian equation x squared over a squared minus y squared over b squared equals 1. And parametric equations x equals plus or minus a cos t and y equals b sin t, where t is an element of the real. So as you can see here, we have p as our general point and it follows what the parametric equations are. With this new information, you can form another key identity. Cos squared t minus sin squared t equals 1. But you may have noticed we have new things, and you may be wondering what cos and sin are all about. We'll look at them and others like them and make sense of them now. Hyperbolic functions have several properties in common with trigonometric functions, but they're defined in terms of exponential functions. If we look at these hyperbolic functions and the definitions listed here, there are two things that stand out. One, their names are quite similar to regular trig names, and some identities, such as this, are similar. The second thing is that their definitions are in terms of exponentials. We can make both these connections and make sense of them if we step into the imaginary world of numbers. Our key is using Euler's formula, which is written out here. E is the base of the natural logarithm, I is the imaginary unit, and theta is the angle measured in radians. Using Euler's formula, we choose to plug in negative theta as our input. We get this. But we know that cosine is an even function, so negative theta is the same as theta. And we know that sine is an odd function, so this is the same as this. We end up getting this result, and this puts us one step closer to where we need to be. Here we have our results from when our input was theta and when it was negative theta. We use both for our next step, which is finding cos theta and sin theta in terms of E. For cos theta, you simply add up the two equations and things cancel out. Be careful to avoid mistakes like this. After that, just make cos theta the subject. You would do something similar for sin theta as shown. If we remember what we just got, we realize that it looked quite messy. The e's had imaginary powers and so on. So let's clean it up by saying theta equals ix and using the fact that I times I equals negative 1. Plug in ix in place of theta for cos and we get this. Do the same for sine and remove all imaginary bits on the right hand side by multiplying by negative I and you get this. We immediately notice that what we have here looks a lot like the hyperbolic definitions from before. Remember the identity cos squared t minus sin squared t equals 1. Let's see what happens when we sub in our results for cos ix here and negative I sin ix here. When you work it out, you reach a rather satisfying point of getting 1. So our results satisfy this. And therefore can be x and y. This is a conclusion that you can consequently draw. So there you have it, some explanation of how this definition came about and an introduction to hyperbolic functions. I hope that you found this video helpful. Come back next week for another.